Hello students, in the previous videos we tried to understand types of rectifier and its working. So we tried to understand half wave, full wave and full wave bridge rectifier. There are few important terms which has to be understood which is related to rectifier, and after that we will go for numericals based on all these three rectifiers. Okay, so the first term is PIV. PIV stands for peak inverse voltage. Peak inverse voltage. Okay, we will take one example so that you can understand what exactly I mean by peak inverse voltage. I will take example of half wave rectifier. I hope you remember the working of half wave rectifier. So in a half wave rectifier, you have a ordinary transformer with more number of primary turns and less number of secondary turn, because it is a step down transformer, and then you just connect one single PN junction diode in series with load resistance across which output voltage will be taken. So this is RL. Okay, so this is P1, this is P2, this is S1, this is S2, and input is applied to the primary. We remember, we can easily understand the working. During the positive half cycle, P1 is more positive as compared to P2. Therefore, S1 is more positive as compared to S2. Diode is forward bias. Resistance offered by the diode is very small. Hence, the entire secondary voltage, that is, we consider it as VM, maximum voltage across secondary, that entire secondary voltage will be dropped across RL. So output voltage is almost equal to secondary voltage. Okay, so in forward bias condition, when the diode is forward bias condition, there is no problem as such. Next, during the negative half cycle, what happens during the negative half cycle? P2 becomes more positive as compared to P1, therefore S2 becomes more positive as compared to S1. Now the polarity changes for the diode. Now the diode is reversed bias and the resistance offered by the diode is maximum, and when the resistance is maximum, the entire secondary voltage will be dropped across diode, as there is no voltage drop across the output. The entire secondary voltage will be dropped across the diode. Now I will take specific example so that you can understand. Suppose VM, that is maximum voltage across secondary, in that example also we took it as 12 volt. So during the positive half cycle, this entire 12 volt will be there across the output. But during the negative half cycle, this entire 12 volt will be dropped across the diode, which is VM. Okay, so this entire 12 volt will be dropped across diode. But if you have selected a diode which can withstand maximum of 10 volt, now what happens? That means the maximum capacity of a diode to withstand a voltage is, say, 10 volt. For example, if we are taking, say we have selected a diode whose withstanding capacity is 10 volt. Now what happens is, in forward bias condition, no problem, the entire secondary voltage will be dropped across output. But during the negative half cycle, when the diode is reverse bias, what happens is the entire secondary voltage will be dropped across the diode. At this point, the voltage drop across diode is 12 volt, but its withstand capacity is 10 volt. So that 12 volt can destroy the diode, or of course the entire circuit. Should that be happen? Of course not. So when you select a diode, you have to select the PIV, that is, you should know the peak inverse voltage. And what should be the peak inverse voltage? It should be equal to the secondary voltage, or it should be greater than the secondary voltage. Okay, so if the PIV rating of the diode is, say, 12 volt. So what happens? Of course, in forward bias condition, that 12 volt will be dropped across output voltage, but during reverse bias this 12 volt will be dropped across the diode. But as the diode has this withstand capability of 12 volt, it will withstand that 12 volt. No damage will happen to the diode. But if PIV is say only 10 volt for that particular diode, of course when 12 volt will be dropped across the diode, that 12 volt will damage the diode. So what is 12 volt, which is VM? What is VM? VM is the secondary voltage of the transformer. That means the PIV rating should be greater than or equal to VM. What is VM? Is the maximum secondary voltage. Okay, maximum secondary voltage. PIV is the maximum secondary voltage. So when you define peak inverse voltage, see how we define PIV. It is the maximum voltage, it is the maximum secondary voltage of the transformer it is the maximum secondary voltage of the transformer which can be withstand by the diode when it gets connected in reverse biased mode. Okay, it is the maximum secondary voltage. As I said, forward bias no problem, reverse bias entire secondary voltage will be dropped across the diode. So what is the PIV rating? It should be equal to the secondary voltage or greater than. So diode, if it has a PIV rating of say 100 volt, that means if it can easily withstand 12 volt also, right? Or if say the PIV rating of the diode is 12 volt, of course the maximum secondary voltage is 12 volt, it will easily withstand the diode. But if the PIV rating you select as say 5 volt, so 5 volt diode cannot withstand a 12 volt potential across it, so it will get damaged. So that is how we interpreted this, that PIV rating should be greater than or equal to the maximum voltage across secondary, which is denoted by VM. So it is the maximum secondary voltage of the transformer which can be withstand by the diode when it gets connected in reverse bias mode. I hope you have understood. The next term is rectifier efficiency. Rectifier efficiency. It is the ratio of maximum DC power delivered to the load to the maximum input AC power applied. Okay, and rectifier efficiency, it is denoted by eta, which is given by DC power delivered at the load upon applied input AC power. Okay, so it is PDC upon PAC, which is your eta. And for half wave rectifier, the rectifier efficiency is 40% in general, and for full wave and full wave bridge rectifier, the rectifier efficiency goes up to 80%. Now this difference is because of the output cycle. If you remember, in half wave rectifier, only one half of the input is rectified, the other half is clipped from the circuit. That means power delivered is only for one half cycle, so it is 40%. And in case of full wave rectifier and full wave bridge rectifier, both the half cycles are rectified. That means power will be delivered on both the half cycles, so rectifier efficiency increases. So rectifier efficiency for full wave rectifier and full wave bridge rectifier, it is 80%, and half wave rectifier, it is 40%. So this is what rectifier efficiency is. The next term is again very important, that is ripple factor. Before going to ripple factor, we will try to understand, we try to remember what exactly we meant by ripple. If you remember, the output of a DC of rectifier is like this. Output of the rectifier is like this. Now, is that a pure DC? Of course not. Pure DC is a straight line. So this is called as fluctuating DC. There is some AC component mixed in the DC component at the output of the rectifier, which is called as ripples, right? So ripple factor is RMS, it is given by RMS value of AC component to the DC component at the output, which is given by, we specify it as IAC upon IDC. I will repeat it one more times for you, that the output of the rectifier is not a pure DC, because there is some AC component mixed in the DC component at the output of the rectifier. That is what is called as ripple. And what will be ripple factor? Of course, how much AC component is mixed in the DC component at the output of the rectifier. So it will be a ratio of AC current upon DC current. So ripple factor is given by IAC upon IDC. And if you design a very good rectifier, if you are designing a very good rectifier, the ripple factor should be as small as possible. Now for a half wave rectifier, the ripple factor is 1.21, and for full wave and full wave rectifier, it is 0.48. So this has to be remembered, of course, and this can be mathematically solved and checked that these values comes like this. Okay, of course this type of question can also be asked. What is ripple factor? Obtained ripple factor for half wave rectifier and full wave rectifier. For that you have to go through a small derivation which can be easily understood by you. Okay, so see how we start the derivation. By total current equation, by total current equation, the total current equation is I RMS is equal to under root of I square AC plus I square DC, AC current and DC current, which is the output of the rectifier. It is a mix of AC as well as DC current. So I RMS, root means square value of current, is given by this equation. Now if you square this equation on both sides, what you get is I square RMS is equal to I square AC plus I square DC. So I square AC is equal to I square RMS minus I square DC. So I can say IAC is equal to under root of I square RMS minus I square DC. Okay, now dividing both sides by IDC. So what I'll get on the left hand side, it will be IAC upon IDC. And what is IAC upon IDC? IAC upon IDC is ripple factor. It is denoted by small r. So ripple factor is 1 upon IDC under root of I square RMS minus I square DC. If you take this IDC inside, what you are going to get is under root of I square RMS upon I square DC minus 1. Of course, when you take it inside, it will become square, divided both sides. So it will be I square RMS upon I square DC minus 1. So ripple factor is given by under root of I square RMS upon I square DC minus 1. Now for half wave rectifier, I RMS is Im by 2 and I RMS and IDC is Im by pi. So if you substitute, these are the standard values for IRMS and IDC for a half wave rectifier. If you substitute this value in this equation, what you are going to get as ripple factor is I square m by 4 upon I square m by pi square minus 1, or this thing can be written as I square m by 4 multiplied by pi square by I square m minus 1. So ripple factor is pi square by 4, pi square, this gets cancelled, pi square by 4 minus 1. Pi is 3.14, and if you make it a square, it will be 9.86 something. So it will be 9.86 divided by 4. It will be under root of 9.86 divided by 4 minus 1. If you calculate this value, this will come around 1.21, which is ripple factor for half wave rectifier. Okay, half wave rectifier. And similarly for full wave rectifier, IRMS is Im by root 2 and IDC is 2Im by pi. So if you substitute this value in this equation, what you are going to get is full wave rectifier as the ripple factor for full wave rectifier as 0.48. I want you to substitute this value in this equation and see whether you get this value or not. Okay, so this is all about ripple factor in rectifier. So what we have concluded is the lesser the value of ripple factor, more is the effective is the rectifier. So you have to make sure that when you design, the ripple factor should be as small as possible. Okay, thanks. Next, we will try to understand numericals based on all the three rectifiers. In that, the first one or the first numerical which I'll take will be for half wave rectifier. Almost same type of questions will be asked either for half wave rectifier or full wave rectifier or full wave bridge rectifier. So for half wave rectifier, I have given you the formulas based on which you can easily solve this circuit. Mostly same formulas will be used. Of course, the formula will change, the same terminologies will be used. The first formula is for transformer. NP upon NS is equal to VP upon VS. Number of turns of primary upon number of turns in secondary equals to voltage across primary upon voltage across secondary. Of course, these values are taken as RMS value. What is RMS value? It is the 70.7% of the peak value, the value of a AC signal at an angle of 45 degree, which we have already studied. Okay, so by this formula, you will be given number of turns, you will be given primary voltage, you should calculate secondary voltage. Okay, once you get the secondary voltage, of course you need to calculate the peak value. Peak value is the 100% value. RMS value is the 70.7% of the peak value. Okay, so for calculating peak value, you have this formula root 2 into VS RMS. That means root 2 value is 1.414. You have to substitute that value and you get the peak value. And for half wave rectifier, peak inverse voltage should be equal to VM. I have already told you what is PIV. Okay, so PIV should be at least equal to the maximum secondary voltage. So this is the formula. VDC is VM by pi, IDC is VDC upon RL. Now the question is asked in this way. In a half wave rectifier, the turn ratio of the transformer is 10:1 with primary connected to 230 volt AC. Calculate PIV, VDC, IDC when load resistance is 500 ohms. Okay, so what has been given? Turn ratio is given, VP RMS is given, primary voltage, and the output load resistance is given, and you need to calculate PIV, VDC and IDC. Okay, so the first thing what we will do is we will calculate VSRMS. So number of turns upon primary upon number of turns in secondary. NP upon NS is equal to VPRMS upon VSRMS. Okay, so what is this? What is NP? 10:1, that is 10:1 equals to VPRMS is given 230 volt upon VSRMS. So what is VSRMS? VSRMS is 230 divided by 10, that is 23 volts. So in the first step we have calculated VSRMS. In the next step we have to calculate peak value, which is referred as VM. So what is VM? VM is √2 into VSRMS. The value of √2 is 1.414, and the value of VSRMS which we have VSRMS which we have calculated is 23. So if you calculate this value 1.414 into 23, the value will be 32.522. So this is, of course, you are calculating voltage, secondary voltage of the transformer. So that is 32.522. This is the peak value of the secondary, which is nothing but VM. So what is the first thing which we have calculated? PIV. PIV is equal to VM, that is 32.522 volts. Okay, so that is the first thing. Second is, what is VDC? VDC is VM by pi, that means 32.522 divided by 3.14, the value of pi. Okay, so the value will be 10.357. If you calculate, you will get this value. Again, what you are calculating is voltage DC, so it will be, the unit will be volt, 10.357. and in the last step you will be calculating IDC. And what is IDC? It is VDC upon RL. Okay, VDC you have already calculated, it is 10.357. and what is RL? RL is 500 ohms, so divided by 500 ohms. So this value is 0.0207, and this value can be written as 1, 2, 3. You can take 3 positions there. There will be 20.7 milliampere. Of course, it will be 20.7 into 10 to the power minus 3. 10 to the power minus 3 is milli, so it will be 20.7 milliampere. So we have calculated IDC, VDC and PIV for this half wave rectifier. I hope you have understood this thing.